I think. Okay, we are recording now. Welcome to the evening of Python coding. This time we will have Lily Sue, who was in Austin, and this is where we communicated quite a bit. And she has been dabbling with AI for quite a while now, and she wanted to talk about Ray, but something more specific than Ray. So, Lily, please present yourself and what you're going to talk about.
Hi, everybody. Yeah, I'm Lily Sue, and I'm going to actually talk first a little bit about my background because I think I have an interesting background that I like to share with people. This will just be for like the first 2 minutes. Meanwhile, I sent a collab notebook in the chat. So your Google Meet chat, if you can please open up that notebook and start running it, because it might take a few minutes just to download the Python requirements using pip install.
I think it's private.
Oh, okay. Let me fix that right now. Let's see. All right, let me share the link again. I think it should be the same link. All right, and then let me present my screen. Okay, so a little bit about myself. So actually, my background is that I have a fine arts degree originally from Rhode Island School of Design. I graduated in 2011, and I was first a sculpture major. So some of the things that define me is that I at one point created a new search term. Am I sharing my screen, or is everybody able to see the Chrome tab?
Yeah, we can see a screen with it seems like an egg, like an egg, or like some chicken in an egg, or
Yeah,
human.
so I
Human in an
created
egg.
this soap at one point in my sculpture career, which is a fetus inside a soap. And I was one of the first people that created the Google search term. And it became more of a product that everybody wanted to copy because it made money on Etsy. And I sold 1,500 of these soaps for $15 each. Another thing that I created as a sculptor was a teeth teacup. This was back in around 2012. This is completely 3D printed through shapeways.com. So it's fulfilled as people are ordering it. So I don't do any work on my side to manufacture this product. There's a teeth teacup with 28 teeth, and there's a teacup for 32 teeth. And as a sculptor, I also got into 3D printing, so 3D fabrication, file preparation for injection molding. I worked for about 8 years with inventors to produce medical devices. What you're seeing is a suture passer that combines two different types of needles for stitching remotely. I've done commissions for artists. I've done jewelry. I've worked on construction-related fabrication, medical devices, inventions, and so on and so forth. An example of something that I might create would be something that is 3D model using computer-aided design on a computer. It might be 3D printed in wax, which is shown here, and then traditional lost wax cast. So the 3D model might look like this, using a tool similar to ZBrush, where wherever you click, there's some sort of 3D object that expands, and then the wax can get lost wax casted. As you can see, there's striations, and this is like a 3D rendering, but the real thing might look something like this. So some other things that I've done was the Nickelodeon logo in 2014, the green globs. So that's a little bit of my background prior to getting into tech. I then worked for T-Mobile. I was one of the key people behind merging the Sprint dataset with T-Mobile on the procurement side in terms of all their spending for network cables and real estate leases. That was back in 2021. And then I worked for Discover Financial Services, helping to replicate their underwriting and to try to find patterns in fraud, as well as helping define the requirements for the data migration, because they were going through the monolith to like API microservices in the cloud. But today I want to talk about a few different things. I'm going to talk about this paradigm that we're going through, where there is this massive need for GPUs due to machine learning models getting larger, the different parallelism techniques that exist. I'm going to do a demo of what distributed computer might look like using Kubernetes. And then I'm going to talk about how Ray can come into the picture. And when you're doing machine learning training with PyTorch, how you could add some tools such as PyTorch Lightning and Ray. So a bit about this paradigm that we're in. So right now, models are getting larger and larger. This is due to the trend of transformer models getting more and more popular with the rise in the popularity of ChatGPT. For just large language models, the size of these models have risen by a factor of 340 times every 18 months. And in contrast to that, the size of a single GPU memory has risen by 1.7 times every 18 months. Compute demands in general, like for machine learning models, have been increasing over 10 times every 18 months since 2010. So in the same period, computing capabilities such as hardware accelerators, GPUs, DPUs have also doubled every 18 months. So basically my point is that there's a massive trend for training machine learning using a lot of GPUs, and there's this need for catching up with having more and more GPUs. But there's not a lot of GPUs out there. Right now, NVIDIA's the only one producing GPUs. AMD and Intel and other companies are catching up as well, that's for sure. But because of this massive need, there's a lot of catching up to do, but we can leverage traditional compute memory on the CPU, and also just the fact that the cost of compute is continuing to lower as years go by. So if nothing changes, if we keep on going at the rate that we're going, by 2026, training a 175 billion parameter GP3 equivalent model would cost somewhere around $3 million. But there are ways to go about making this easier. So this is where like the parallelism solutions come in. And today I'm going to talk a little bit more about how this works. But first, I need to talk a little bit about the terminology that we're going to use. So when I talk about a node, I just mean some form of computer. That could be, sorry, hold on a second. So that could be a iPhone, that could be, when I say a node, that could be a Raspberry Pi, it could be Arduino, it could be a ESP32, it could be a virtual machine, it could be a satellite, it could be a router, it could be a server, it could be your desktop computer, it could be your laptop. So that's what I mean by a node. It's some sort of kind of computing device. It has to have network communication in the terminology that I'm going to use today. And a cluster, when I talk about a cluster, that is like a grouping of, I'm just going to say like computers, but a grouping of nodes. So just give me a second here. I'm going to actually switch to, let me think. Yeah, so I'm going to keep on going with my slides, and So I'm going to talk a little bit about why we're talking about Ray today. So right now, what's happening is that with these larger language models, if you want to train them yourself from scratch, one model, if you have like tens of millions of parameters or more, it's going to be difficult unless there's some sort of compression happening. And then even with the compression, billions of, I think after about like 10 to tens of like billions of parameters with these machine learning models, even to inference them, you're just not going to be able to fit them onto one computer. And the most efficient way right now to train or inference these machine learning models is on the GPU. But because these models are so large, we have to fit them in a number of different ways on multiple nodes. So what Ray does is that it's an abstraction on top of these different nodes so that we can use Python to more easily control how we process our compute. Very similar to Python multi-threading techniques, except instead of the threads running on separate kernel functions, like in their separate containers inside different threads on your computer, you're running on multiple computers, and Ray takes care of the networking for you. So now I'm going to give you a very low level, or at least I'm going to attempt to give you a low level demo of what the lowest level would look like if we didn't use Ray. But I'm going to switch computers real quick because the computer I've been using, it just, it's not where everything else is running, but I just wanted to do the demo, the PowerPoint real quick. Okay, so I'm back and I'm just going to share like another window right now. Hold on a second. Let's see. Okay. So can everybody see my Mac terminal?
No.
No.
So
Okay.
no.
Let's see. Hold on a second. I'm just going to change my settings real quick.
I'll complain about Ray in the meantime and say, where is the Python 312 binary? I had to go back to 311 to install.
You're lucky. I'm stuck with 310 in most of the code I have.
I had to go, I was on 3.8 or, I mean, I was way behind until I realized I couldn't run Django 5 without 310 or newer.
I'm almost embarrassed to say I have things that are very important that run on 2.7 and I cannot migrate. So,
No shame.
Sorry about that. Still working on it.
Well, I'll talk about my introduction to Python. So in undergrad, I had signed up for a Visual Basic class that these were
Rebecca,
normally held
Rebecca,
in the day. Yes.
Rebecca, this part is being recorded. It's like,
Okay.
let's keep it on topic as much as possible. We'll later can talk about other things. Let's Lily solve the technical glitch.
Okay.
We'll be okay. We tested it before, it worked. So
yeah, it's my Mac terminal that I'm trying to share that I didn't try out before.
you'll have to share the screen to make it. It has an option of when you share a screen, when you share, you are able to, when you present, it asks you what to present. So you just have to choose the correct window. You can share the entire screen or window. And it has a tab there when you try sharing.
Yeah, it has to do with my like privacy security for the like my Mac. Like it's
Yeah, it will show you only some things. This is what it will allow. Can we do it on a different, like on a Jupyter notebook? Because we had a Jupyter notebook code. Can we jump to that?
yeah, let me just
Let's try again. If it doesn't, we'll jump to that.
yeah, let me just share my Jupyter notebook because I don't want everybody to be waiting on this. And let me just try it again real quick. Yeah, it's not letting me, so I'll just share the Jupyter notebook. Okay, so either way, let me just show what I was trying to demo. Hold on a second. So basically what I was going to show is that I was going to type what I would generally type in with on my Mac terminal is create cluster config, and then I have a file called 3workers, and then let's see. So it would look like this, and then whatever my file was, which is 3workers.yaml. So then after I type in this, the result that I would be getting, it was going to look something like, I mean, this is, well, like this is the YAML that I'm running. So what kind is that it's a framework that allows me to run multiple Kubernetes, sort of like allows me to access Kubernetes beyond just Minikube. Kubernetes is a framework that allows me to orchestrate multiple nodes at one time. We just discussed what nodes are. So the node that Minikube allows me to run is just my computer, but Kind allows me to run not just my computer, but split my computer kind of like into as many different nodes as I need to in order to simulate the Kubernetes framework of adjusting around and configuring and working with different nodes. So when I have a file like this in a YAML file, it lets Kind, the framework, to let Kubernetes like understand that there's these three computers. I have one node for control plane, one node for worker, one node for role. So let me just exit out. And then next, what I was going to do is I wanted to show you that I had, so now that like we have established that I have these three different nodes, then
You basically created the virtual cluster on your machine. Am I correct?
exactly. Yes, you're correct.
Okay.
And then what I have on my file system that I was having trouble showing is that I have a, let me see what I have. So I have these other files that pretty much have other configurations like in place, very similar to this one. This is my my Redis dash deployment.yaml. So just yeah, what I'm doing on the side right now is I'm opening up in Vim these files. So I'm running this command and then opening up this file, and then so I'm showing that to you and then exiting out, and then what I would do after that would be well, I would want to run this as a command. So in my code, it's not formatting correctly, but it takes time. So I don't want to waste people's time to.
Lily, one question, just to explain for people, Redis is a database or a key value store that you're installing as a cluster, correct or incorrect?
Correct. Correct.
Okay.
So what's going on in this deployment is that I'm creating like a plan pretty much that once I run this file, it's going to automatically spin up a like a kind of like a brain, like a computing instance where the environment name is set to this like Redis host. And I already have a Redis account right now, and it's living in this place in the cloud. So what that looks like is, can anybody see this tab that I just opened?
Yeah,
Okay,
PyDem,
great.
PDEM.
Yeah, great, awesome. Yeah, so this one has like an endpoint that is connected to. I could use a CLI for this, but you can see that this is my public endpoint. So this is a storage, like a key value system that is stored in random access memory living on the cloud. And supposedly, like if I were able to run this, this is like a connection point between the node that I set up on my local computer with this connection point. But this is not the only connection point that's actually needed, unfortunately. So then if I were to run this command, then I know this formatting is terrible, but I don't really have time to set up the proper formatting. Then this deployment gets run, and then I will continuously have a node that's running that is like a computing instance that has this container, which has this like connection to Redis. And then next, because like so right now, like I'm talking, my Redis is going to be the control plane. And what's happening here is that in my Ray example, what's going on is that we have these 4 different nodes, right? So in order to distribute anything, like we have to plan this out. It's not like we have these three computers, 3 nodes, and like what are they going to do, right? So we have what's happening with this green part that's different from the rest is that this is like kind of like the Eye of Sauron in a way, like the like main kind of control. This is called the control plane that is planning out what the other nodes are going to do, but it is also its own node. And this paradigm or this structure exists in a lot of different ways. Sometimes in machine learning, there's a parameter server that controls multiple different distributed nodes. In Kubernetes and in these low-level concept is considered a control plane. I'm not going to go too much in detail with this, but after that, so you saw what the control plane looked like. Then I'm going to show you what another file looks like for us. So I just talked about the control plane. Then I'm going to talk about the workers. So one of the workers, well, the worker deployment that I have is going to look something like this. So I'm just naming it a PyTorch worker. It's not actually going to be PyTorch. It's really going to be this like Python file that I'm running. I made a connection to like the Redis like environment, but it's actually tied to another container, which is like a Docker instance that I'm running. And that Docker like image is called, what's it called? It's actually called Hello World Redis right here. That's my Docker image, and then like on my Docker hub, let's see, I can find like I have like this image living publicly in my personal registry, and then
So for the beginners, I'll slow you down a little bit. Docker is basically a virtual machine, like a compute type of virtual machine, and you have it somewhere that you can actually replicate this machine, and you replicate it in each one of your workers, correct?
I'm replicating 2 of these workers, yes.
Yeah, but you're using the Docker, the virtual machine. You basically filling out your workers, which are nodes, with as if they have a hard disk that's similar to this Hello World Redis, correct?
Correct, yes.
Okay, just trying to explain for the beginners, because
Yeah.
sometimes there are people who the words, the buzzwords kind of go over their heads. I want them to get something out of it. Go ahead, sorry.
Yeah, that makes sense.
Also, a request for font plus plus in the chat.
Sorry, what does that mean?
Bigger font, if you could.
I don't think I could do bigger than this.
You can use you can zoom your screen and get the you can expand your screen.
I think if I get bigger than this,
No,
that we're not going to be able
what
to
I'm
see.
saying is I apologize that I'm speaking over you, but one at home can increase the size of their screen, so that you can increase the zoom of the browser and adjust the font to your liking. And I'm going off now.
I see, thanks. So, so besides running these deployments, which I do, Redis, I do pretty much kubectl apply force, and then this this file, and then the other file that I had was this like PyTorch worker. Besides that, I also had to, it looked like something like, besides these 2 commands that I needed to run, besides I also had to expose this, what do you call it? Hold on. It's like a port that I had to expose in order to make sure that the 3 machines can talk to each other. Because when you think about how this would work, how are they going to communicate to each other? I mean, like the only way we can really do that, I mean, normally these days, is that they have to be kind of like routers kind of system. They have to communicate via Wi-Fi. But then, with, connected to being connected to the internet, each node has its own IP address. They, as a cluster, they all have their own IP addresses, but they have a different port. So we're kind of going into networking with, IP version 4 class, C, each, like, in order for them to communicate with each other, like they at least physically have to have like a telephone cable. If they don't have a telephone cable and they're, they're connected via the network, they have to have a unique port that they could talk to each other in. So the head node is talking to this Redis, that's connected via the cloud in that URL that I showed you. But with each other, they're talking via a particular port. And this port is different from the URL that I shared, and that URL actually has a port of its own. So as you can see, like there's a lot of complications with these particular concepts. So besides these 3 workers, what I also have to set up is it's like a cluster IP that would be able to expose these ports. Without that, these different nodes cannot be connected. And what that looks like is, let me just pull that files. So I have another file called, so it doesn't have to be a load balancer, but this is one. And you can see that I have, a port information right here. And besides this, I also have to run a command to make sure that the nodes are exposed in this particular port and not all ports, because if it's all ports, then there's going to be security vulnerabilities. So Longpoint kind of, into like there's a lot of different complexities with just trying to communicate with each other. So, and just to make it a little bit more clear, going back to the point that I glossed over with the Docker file. So what I actually have is that, so the head node is the Redis store, and then each of these worker nodes, they have their own virtual machine, like their Docker file. Inside these Docker files, they have a operating system that's running. The operating system has Python downloading. That Python is running a particular command. It's calling like a hello world, and this hello world, it's getting printed and sent whenever these workers are online. And when I have to have some sort of command to make sure that once the Python program runs in this Python virtual environment, this virtual environment that's running Python, that like when it doesn't necessarily shut down right away, or when it shuts down, it has to be a specific length of time. And then the only way that I can see that what's actually happening is through a logging system. So this is a lot of work. That's where Ray comes in. And now I'm going to run through how Ray can be used properly. So I'm just going to...
Lily, slow down for a second. So you showed us how to create a cluster that sets out a database and some compute nodes and some master, something like that, so far. This is what you do. You did it so far using Kubernetes, Docker, and I think these are the tools that you used. You are now gonna use Ray on that cluster, or are you using Ray differently than what you just set up?
I'm going to use Ray completely differently from what I just set up. I'm just running a very basic class, a class called child normal. And
Okay. So far you've shown us how complicated it would be without Ray. Now you're showing us how Ray simplifies everything, correct?
Right.
Good.
So
now let's continue.
Right. So now I'm just running through this Colab notebook that I shared in the beginning. What it's doing is that it's just installing Ray as a Python pip install. It's just a Python library. And before I even run anything related to Ray, I'm just going to run through like a basic Python class. So basically, this is just a class that has a like child normal as the definition of as the class. We have these methods. So the init is the constructor method, and it is automatically invoked when a new instance of any class is created. So it's always automatically called when a new instance of child normal is created. And the items inside there is a name, and there's an age. I'm doing this one thing where I'm cycling through these names so that these names don't get repeated, because I don't want there to be two Brendas or two Katies. So then later on in my demo, it's obvious what's happening when we don't have duplicate names. So self.name assigns a name to the instance's name attribute. And then let's see, child.normal.name index, it accesses this class variable called name index, which starts at 0, and it keeps track of the current index of this names list. So that's how I'm going to cycle through them and remember which one I'm at. And then it's going to be incremented by 1 in the future instances, and it's doing that right here. And then the modulo, what it's doing is that if we're at the end of the list, it's going to go back to the beginning of the list, so then we don't have an index error. And then I have these attributes. So the attributes are the name and the age, the name. Yeah, I kind of just said like it's a list of names, and then you have the age. I'm assigning a random integer from 1 to 14. And then I have a grow method. It's an instance method, and it increases the age every time it's called. And then the greet is just prints out the age, like simulating a greeting. So now I'm accessing what the more, like I'm making an instance of a child normal. So by creating this instance, child normal underscore 1, by like creating this variable, like it instantiates the name and the age automatically. And then I can pull out the name and show that the name that, that got picked was Cynthia, which is the first, index 0 of this list. So just to make things slightly more complicated, I'm gonna create 5 of these. So now I have a list comprehension. It's child normal for I in range of 5. So 5 times this child normal gets called, and each time it's cycling through that list of names and it's coming up with a random age. So going back, an actor, like just the general definition of that as like a computer science idea is that it's like a math model for kind of concurrent computation, and it's like the basic building block, and that's just like the basic name that is being sort of communicated when talking about concurrent computation. So this actor can make local decisions, it can create more actors, it can send more messages, it determines how to respond to the next message when received. And then for the case of Ray, it's what's considered like a stateful worker. So it saves something. Some, like you have data in there, it's a yes or a no. It's gonna, if it ends in the past, whatever you did as a yes, it's gonna keep it as a yes. It was no before, it keeps this as no, like that, like whatever it is that's stored in there, it's being saved. So I'm just gonna go through. So what it would look like, the previous class will look like in Ray. So notice that I have this one extra little piece that's added. It's ray.remote. This is what's considered a decorator. By having this, just this very one line piece of code, it actually changes up the whole entire concept. Now we're accessing that Python library, Ray, that we just installed. So now, even though we're calling a child Ray class, this becomes like a Ray object. And you can see that I have something a little bit more simplistic here that is a little bit different from before. I stopped, let's see what I do. Yeah, the index is no longer there the same way, starting at 0. Let's see. So it's just like is let me just run through this.
It's like your child normal, but you instantiating it like you running some sort of Ray decorator on top of it. Am I correct?
Right.
Okay.
So if you run through everything that we did here, that's what you'll notice is that it's slightly different here. When we're calling the method, we have to do a ray.get. And then here we're calling a child ray.remote. This is the difference. And what we end up getting is that when we're accessing trying to access the same thing, we're getting these IDs. So this ID, these are like cryptic, like alphanumeric strings, and they are unique identifiers for these like actor instances. It's what allows Ray to manage and access actors when it's across clusters. And what's happening is that each of these instances that we called, it maintains its own state. It just remembers what it is that is saved in terms of the name and the age. I wasn't able to do the same thing as previously with the index, because previously in the class, the type of access is like open, and then like with the Ray instance, because of this, like what I kind of showed with the ports, it's not necessarily open in the same way anymore.
Okay, you'll have to stick around here for a second. Go a little bit down and let's try to explain this a little bit. So you created here an array of Ray. You keep on moving it. Yeah, you keep on. You created an array of 5 Ray processes, correct? Or actors, or whatever you call them, correct?
Right.
They have not been executed yet, correct? Or have they?
I haven't accessed them yet, but this is what the object looks like. But if you were to look at what, yeah, I haven't, right. If I were to print out this child normal file, let's see. It would look something like this, which is different. Yeah.
Yeah, it's because the computation didn't start. Sometimes they call it lazy computation. It's saying, oh, I need to do this and this and this and this and this, and the machine will start doing it whenever it has time or whatever you tell it to. Until then, it just kind of registers things it needs to do. So Ray is built like that, correct? It's like you just defined what it needs to do, and later you tell it, now do it, correct?
Yeah, I guess so. You could think of it that way.
I know that Dask and some other system like Prefect, they do the same thing. So I assume it's very similar here. Okay, so this part is explained. Those are objects that are sitting on some worker somewhere, or the Ray created the worker for you.
Right. In this particular case, we're not assigning them to different nodes, but they're living as these unique identifiers. And because I assigned this variable to each of these 5 instances of the class, it assigns these unique identifiers in case we need to access them in the future.
Okay, perfect.
Yeah.
So now you're going to run them?
Right. So I run them in a list, and the only way to get them is a little bit different. We're using ray.get. And then we're going to also call them with, if we're calling greet, we got to do a dot remote. And that's how we would access the objects, well, like the attributes that are stored inside of the class. So now we can get the same thing as before. After that, let's see. I'm going to take only one of them. Like the first, I'm going to take Cynthia, who's age 13 right now. And then I'm going to, let's see, I'm going to print out like the age of just one of them. But I'm also going to run grow. So if you remember grow, it increments the age. So it's growing this instance of like the Ray child, and it's growing this, child Cynthia by 1 age at a time here. And what I'm showing here is that it would be happening separately from the rest if all 5 were to be running at once. So the next one just shows what's happening previously, but for all 5, just incrementing by 1 age. So you can see Cynthia started at 7 and she grew to 8, Mabel 1 grew to 2, so on and so forth. So basically, you know, each one of these instances, they are they have a certain state. They have something like a function that, you know, acts on whatever state that was saved, and then they do the computation separately from each other. Okay, so that was this notebook, and then I'm going to share the next notebook. Okay, so I shared another notebook, the link in the message. So this notebook is going to install a couple other libraries, but first I'm going to just show what the data set that we're running looks like. It's a pretty small existing like data set for the measurements of iris flowers, and the whole point of this data set is just to classify what kind of, I think, like whether or not it's an iris or what kind of iris it is, of iris flower.
It's a very famous machine learning exercise. It's one of the first things that people try to do. Usually, it's like they use clusters or some other classification methods. You have information like leaf length and stuff like this. Ah, here it is.
Yeah, it doesn't have a lot of data. It's just these petal kind of information and sepal length, sepal width. And then we added this target. That's another column we added. And this is determining what like class it pretty much belongs to. And the whole objective is to classify what kind of like iris it is.
So your target is the label you put on the data, correct? You have a record, which is sepal length, sepal wide, petal length, petal wide, and then you have a label. This kind of iris, this kind of iris, and how many classes you have?
I believe I have 3.
Okay. So your machine learning task should classify one of those 3 classes anytime you give it a record of 4 numbers, and it will tell you what kind of iris it is. 1, 0, 1, 2, 0, 1, or 2.
Right.
Am I correct so far?
Yeah, you're correct.
Okay, good.
All right, so to do this in a 3-layer neural network, using just traditional PyTorch, basically what we're doing is that in order to run PyTorch is already installed. That's why we didn't spend a lot of time in Colab to install it. So we're creating a class very similar to how we created a child class, but we're inheriting this NN module. The NN module is what allows us to access PyTorch, all the PyTorch functionalities. And then we're taking in 3 parameters. the input size, the hidden size, and the number of classes. So we define the number of classes to be 3 later, like you'll see that. The hidden size, that's something that we can determine. It's what's considered like a hyperparameter that we can try to figure out what's the best kind of like a setting we could create to improve our model. And then the input features have to do with like the data that we're inputting. So, and then the super 3-layer perception, it's calling the constructor base class in a module which is PyTorch. And then for each of these 3 like linear layers that you can see right here, what we're doing is we're just performing this like linear regression, like a line function, y equals wx plus b. W stands for weight and B stands for like a bias. So the first layer is transforming the input to a hidden layer size. And then ReLU is the activation function. It's kind of like a filter so that it converts this line and it's like a threshold. It's cutting off at a certain point because this is like we're classifying something kind of like yes or no, you know, what class it's in. We're using this particular activation function to determine like whether or not we want to take a result. We might reject the result and not let the data continue. What it does is that introduces nonlinearity. Otherwise, if you don't introduce that, it's the same thing as just like running linear regression. And then, so the second layer, we produced a hidden layer of the same size. And the third layer transforms whatever compute that we did like in the middle into the number of classes, which is 3. And then the forward method, what it does is that it's passing the input data through the network's layers to output the prediction. It's kind of like running the operation. So like during this operation, the input data is sequentially processed through the network's layers. It computes a weighted sum and it applies the activation function, which is the ReLU, to produce the prediction. So when we run the model, we initialize the model. So 3-layer perception was our class, and then we input what we want. Our input size is going to be 4 because we have the 4 columns. Hidden size, we're just making this up, but 100 is something that is just like a generic something that is working. And then criteria cross entropy, it's a loss function. So it determines whether a prediction is going to be good or bad. And then the optimizer, it like updates the model's parameters during training. So the learning rate right now is at 0.003. And then it tells like the weight and bias that we're changing up. Like think of like when we're kind of computing a linear regression where it's a guessing game of what the weights and biases should be. And we're computing the difference between our prediction versus the actual of the weights and biases. And then the atom optimizer, it's taking what we learned and it's calculating the acceleration or which direction we should go based on the errors we made in the past. So next, we're running a training loop because basically with the neural network, we have to compute something multiple times. We compute something once, we see that we're wrong. By taking the derivative of that, of how wrong we are, we can tell in which direction we should go to further improve. That's why we have to iterate over and over again. So that's why we're using something called epochs. That's like 100 times we're going to go through in a loop until we find the best answer we could after 100 times. So when I run this,
just a few things. The epoch is going over the data one time. This is what's called an epoch. So you said go over all of the data that you're going to train 100 times. This is what you're asking here.
Right.
Okay. Go ahead. Sorry.
It's okay. See, so we're we're going through the data 100 times, and then let's see.
You can skip some of this code. This is too low level. Today, the code is usually much more condensed when you run neural networks. So it's good for training, but this is the purposes is mostly Ray. So
Yeah, so next I'm doing pretty much like a very similar thing, except we're using PyTorch. PyTorch Lightning. So what PyTorch Lightning is that instead of having to do this for loop with the epochs, just if you could focus on this part, you notice that instead of doing that, we're just adding some additional methods. So after forward, we have some other methods here. We have a training step and we have a predict step. So we pretty much modularize and condense that for loop, double for loop that we had, and we're just running that as a function, and that's what Lightning allows us to do. And in this way, we can better track our our results in terms of experiments, because we're running this model multiple times, and it's going to allow us to so we ran that model once, but we ran it 100 times, right? But in a science experiment, we might run this model like 10 times with different parameters. So PyTorch allows us to do that, but allows us to do a couple of parallelism techniques. So let's see. I'm gonna skip. No, like with this, I'm on the PyTorch Lightning equivalent above. Let's see. So basically, I didn't turn this on. I can't really turn it on because I'm not on a system where I have multiple computers to train on. But what PyTorch Lightning allows you to do is some data parallelism techniques, and a data parallelism technique that PyTorch uses is called distributed data parallelism, or DDP. So it allows you to specify multiple GPUs to run your data across. Each GPU has the entirety of your model, but then it's running through a different portion of the data. To be a little bit more specific about that, the data, when it's split across multiple GPUs, what is actually splitting is called a mini batch. And then each GPU will perform their own forward pass on their own unique mini batch. I mean, the forward pass, you saw the method earlier. So what happens after you compute the forward pass, what that means is that you're computing a different loss value, that loss value being the error. And then after that is being calculated and the derivatives being developed, that gets like filtered by the optimizer. We have that optimizer, and during that step, all the GPUs have to align and get in sync and talk to each other, and determine what the average of that global gradient is. And then that's going to be updated, and all the GPUs are going to align and say, okay, the next step, we're going to use this particular weight. And then the whole process goes through again. So after every epoch, the GPUs have to come back and talk to each other. That's DDP, distributed data parallelism. PyTorch also allows you another functionality called FSDP, which stands for fully sharded data parallelism. And what happens there is that the model is divided upon multiple GPUs, but it's not in such a sense that layer 1 lives in GPU 1, layer 2 lives in GPU 2, layer 3 lives in GPU 3. It might be something like layers 1 and 3 lives on one GPU, layer 2 lives on another GPU. There are different ways to go about it. So the way that the model is getting split up, it could be split up in terms of layers, but we can also think about it as different stages or groups of layers. And what's getting split up is the weights and biases again, and the optimizer. And the way that it's able to do that is that it's also aggregating and then distributing the result back to multiple GPUs. And the sum of each gradient is getting computed after each like epoch. And both with distributed data parallelism and fully sharded data parallelism, this is done through another framework called NCCL, and that stands for NVIDIA Collective Communications Library. I think there is an equivalent for AMD as well, but that's like the common concept in like white paper literature. And the way that it's aggregating, it would be called OutGather, just to throw out some terminology. And then when it's distributing out information, so for FSDP, all the nodes are going to gather together their results, and then when all the nodes decide what the average is, like the node the piece of the model that needs that data, the data is only sent when where it's needed, and the rest of the data, it gets thrown out. And that's called reduced scatter, just to throw out some terminology. So this is just PyTorch with PyTorch Lightning. Just simplifies things a little bit, and then has these parallelism techniques. Now I'm going to talk a little bit about RayTune. So RayTune adds another layer on top of that. What it can do, so going back to, okay, we have the very base idea of nodes talking to each other. There's the networking. There's how do the message get communicated. So that's a general concept of Ray, but I'm going to say that because of that being the major concept of Ray, this could be used in a lot of different ways. It's kind of like how the technology of cake mix got developed. The whole technology of cake mix is just that you have flour and you have salt and you have sugar and baking powder, and then you combine those into a box. So if you think of Ray as the cake mix, so what Ray did in the past years is that they originally started off being like, oh, we're just going to focus on reinforcement learning because this is all about communication, fast communication. Doesn't have to be a lot of data, but it could be a lot of data because in the market, there's already MapReduce and Spark, and these are fundamentally big players on distributing a lot of data. Ray can do that as well, but there are already fundamental data structure type technologies that exist in the space. So what Ray did is that now they're kind of saying, oh, we could do cake mix, but we could also do muffin mix and mashed potato mix and pancake mix. So RayTune is one of the so there's like RayTune, there's RayServe, there's Ray Cube Ray. So there's a lot of different technologies that Ray is kind of packaging with this particular framework that they've developed. And the framework is just about the communication over sort of these containerized node workers using Python. And so what RayTune specifically does is that it defines a search space for hyperparameters. So for example, that learning rate that we had, 0.001, that could be changed to better experiment on. So we could experiment on different scales of learning rate. We define a kind of search space, I guess, like a range in terms of changing up the learning rate, changing up the hidden size. These are just the two. I made a very simple model for today's demo to show just like the basics that you could tune. There's like more things you could tune. You could change the optimizer or just play around with different searching for different parameters that you could tune to make your model work better. So that's what RayTune does. It makes it runs through that loop. Like it uses PyTorch Lightning is running through that loop for you, but as you're running through a loop, it's logging for you these different different parameters, and it's also implementing a Asha scheduler. And what this is a if it's like found that it like the parameter is not as efficient, it stops the less promising trials early. Like if it's underperforming. So that's what it's doing here. And like PyTorch, so that was Ray Tune. So Ray Train has let's see. So Ray Train, it can work just with PyTorch without PyTorch Lightning. So because I didn't want people to get too confused between like where Lightning ends and Ray begins, because they can be tightly coupled, you know, a lot of documentation that's out there. So I showed like here in Ray Train how this is working. So what it's doing in this piece of code is that it's configuring the training job with scaling config. And then specifying the number of workers. It's specifying the number or whether GPUs should be used. Here, scaling config right here. And it also supports DDP, but you know, I'm just not using it here. So RayTrain can be used with RayTune without PyTorch. PyTorch Lightning. There's many different ways to go about it. This one is just executing one single training job instead of previously we executed multiple jobs, because with RayTune it's all about iterating, just to show what can be done. And then I'm just gonna, so that's pretty much what I have in terms of my demo. But I did want to just clarify like a bit about people who might already know a little bit about distribution in this space, because there's a lot of like MapReduce has been used a lot and Spark has been used a lot in the space of just like data science. And I think one question that comes up that I just want to answer is how MapReduce is different from Ray. So MapReduce is a programming model for processing and generating big data sets in parallel. And it's this like distributed algorithm that can distribute data on multiple nodes in a cluster. It's doing two things. It's doing map and it's doing reduce, as the name says. So with the map, it processes and transforms input data into key value pairs like a dictionary. And then with reduce, it aggregates and processes the results of the map to produce the final results. So it's very structured in terms of how it's doing just these two key tasks. And it's all about like batch processing of tasks. Whereas Ray, it's a little bit more general purpose, like I mentioned with the cake mix, muffin mix like concept. It's more of a general purpose framework. It's more specific to use people who are already using Python. So it was always meant for reinforcement learning and like working with like machine learning, like AI. It could be a large amount of data. It doesn't have to be a large amount of data. You can decide it's flexible. And like if you're programming in Python, making some kind of like a migration, like porting over some of your code to use their framework. Similarly with Spark, it's also like a batch processing paradigm, but Spark is both batch processing and stream processing of large scale data. I think people might be familiar with like PySpark Notebook, Spark Notebook, which is a Jupyter notebook that runs on a distributed system and works fairly well for large scale machine learning tasks. So how it would be different is that I can imagine that you could use the two in parallel, where you could finely tune which part of your machine learning model is going to be distributed and which part is not, a lot more easily using Ray than with Spark. And Spark is like more familiarly like used with like ETL jobs. Like it's known for its like optimized execution engine. whereas like Ray is more like fine grade task parallelism. And it has like a lot of libraries that exist for machine learning workflows. So I just want to talk about the difference a little bit. And then the third thing that I like, the very last thing that I want to talk about is that like, besides what I talked about, I've really just talked about data and a little bit about like data parallel. I mainly talked about data parallelism with distributed, what is that, DDP, right? So, and then FSDP, which is like fully shared data parallelism and data parallelism. But there's also like with there's also tensor parallelism, because when we are distributing our work across the GPU we can be configured to store the data instead of in a matrix, but like that's 2 dimensions, we could store in a 3-dimensional matrix. That's tensor parallelism. And on top of that, there's also like 2.5D like parallelism, where you're doing some kind of like rank related matrix, like kind of rank ordering type of techniques to reduce the storage size. If you don't need to access the data right away, you could like pull out the data, eventually just running it through a matrix function. And then so besides tensor parallelism, there's also pipeline parallelism. Pipeline parallelism has to deal with, so you have multiple threads that that are like running, and you need to access data from an earlier thread, and there's overhead time that exists. So you could shorten the overhead time by while, like, if you know that the next thread is going to be used, you could turn that on earlier so that it's loading the data while another thread is running. So then you could save some time. It's like that, like general system is more like a tiling technique. So there's data parallelism, model parallelism, tensor parallelism, and pipeline parallelism. And beyond that, there's also CPU offloading, which is, so GPU, we're used to buying computers. GPUs usually only have what, like 8 gigabytes, base model, like base, laptop model that you could buy from a store, and then 16 gigabytes. Whereas like your, SSD or HDD has like, 1 terabyte, or at least like 256 gigabytes, right? So with the data that you're not using on the GPU, you can offload the parts that you don't need into your CPU. So that's, offloading. So these are the different technologies that are out there. Something new that I also discovered is Intel has like a CPU extension. I haven't been able to get it to work well, but it could be because my model is just too small. There's like overhead in terms of configuring it. But if you just run these two, let me just share this notebook just for the sake of like trying it out. So I'm going to share this. So in this notebook, I'm just running some Linux commands to show me what is actually behind the hood of this Colab notebook. And we can see that there is an Intel Xenon processor behind this. So because of that, there's a PyTorch extension that leverages like an Intel optimization. So I wanted to run it and try it out, and I did a benchmark. I think you probably need to have like a lot of like data for this to be worthwhile. And beyond that, what it's doing is that it's doing some mixed precision related compression. You only need to do mixed precision. People need mixed precision when they have a lot of data, and they want to compress. They have a need to compress, and they're okay with letting go of some accuracy. One example of this is that certain luxury cars have like a gaze detection. So they notice that your eyes are not on the road, then there's like a beep on the car. So they might need to compress that model to fit it on a car, so that the data of how they're detecting your eye gaze is always stored in the car and never sent to BMW sent to like Lexus or whatever. You don't want the data, you know, exposed due to privacy issues. So that model has to be small enough so that gets compressed in a car. And they're okay with the accuracy being like not so great because like maybe it's just a very small beep and you could turn it off. So so it doesn't have to be a perfect model. They're willing to sacrifice accuracy. So that's like a real life situation where you need to compress the model and you could use mixed precision. So like this Intel CPU optimizer is like accessing that particular concept when you're running that particular extension that works with PyTorch. I was trying to do some benchmarking, but I didn't really spend a lot of time on this. And because my model is just like 3 layers, and the neural networks I was talking about, you know, they have a lot of layers and a lot of parameters. Today we dealt with 4 parameters, but the models that I'm talking about, therefore, you know, like 50 billion parameters. How are you going to deal with that? So that's like a different beast. And because of that, this might not apply, but I'm showing here in a notebook how you could at least run it without producing errors. So yeah, that's pretty much everything that I have here.
Okay, so first of all, let's give you some applause. But then will be questions. Don't go away yet.
Okay.
Some questions have already been at the written in the chat. So Rebecca, I can read your questions, or you can ask them yourself, whatever you prefer. I'm going to start reading them. You can jump in and stop me. So Rebecca asked actually several questions. So ReLU is like a baseline cutoff between the groups. So Lily? The ReLU activation function.
So all your data is being passed through like your linear, it's kind of like a linear regression function, right? Wx plus b, your basic line. So you want to have some sort of threshold that says if it's going to be close enough to the line, maybe, then yes. And then not so close to the line, like below the line, then it's no. So you want some sort of threshold. The ReLU is there because we're doing like a classification model, yes or no. This is not like, you know, housing prices, like 0 to 100,000. This is more like, you know, black or white, like yes or no. Because of that, we're using ReLU. ReLU looks like, so it's like a cutoff, and we're processing all the data all once each time we're running through something that looks like this. So if the data computes to like beyond the threshold, like so anything below 0 would be a different class. That's how it's thought of. And
Okay, yeah, that sounds very familiar to how I would assess PCR reaction to eliminate noise. You would have signal to noise, and you wanted to eliminate as much of the background so you could get the what was it? It was a derivative, but it had to do with the change in slope that you were trying to capture for detection. So this sounds pretty much similar.
mm-hmm. Yeah, if we don't have an activation function, then we would have just been doing linear regression this whole time. There would have been no difference.
Yeah, this is more like a pass or fail question, like a yes or no question, pass or fail, where I was just eliminating background noise to get an actual measurement of amplification. But it looks like the same principle.
Yeah, it's not like anomaly detection. That's so it's not necessarily like, it is a cutoff, but it's not necessarily cutting off just the extremes, if you know, get what I mean.
It's
Yeah.
amazing.
Yeah, it's just different language, but it's, yeah, okay.
Amazingly, this is very similar to how a diode works. So like in all electronics, all transistors. So the concept has been a while in electronics, but now it comes back here in neural networks. But there are several activation functions. Second question that Rebecca asks is about the epoch equals iteration.
Yeah, right. When auto like we pass through all the data through the model, and then it computes the result. That's one epoch. And neural network, we do this 3,000 times. We do this 100,000 times, because each time we're computing the gradient being the acceleration. So like maybe not like so with this parabola, for example, then when we one iteration is we can plot it on a graph like this. When we compute the derivative, we can get a acceleration function to know how we can change our weights and our biases in that wx plus b, how we can change that to decrease the amount of errors that we're getting. So that's why we're running through multiple epochs.
Yeah, so
Okay.
let's go back again to epoch. Epoch is the name of running over all of your data once from start to finish. And the data can come in random order. Typically, it comes in random order. But once you finished all your data once, then you call it an epoch.
Right.
Okay, so is this like if you keep repeating the iterations that you're fine-tuning the result to what's actually there? Because
Yes.
this reminds me of what we would do, or what the imagers would do in nuclear medicine. So you would run something 1,000 times to get to fine-tune the reading, so that I guess it would clear the images. This came in handy with like partial volume correction, is if like we were doing brain scans. So if the subject moved, then that would change everything. So you're trying to create an image, a 3D image. So sometimes you would have to follow the dot, but to make the image clearer, you would have to run these. Well, you call them epochs, we call them iterations. We just have to run through the equations several times, recycling the result to get the best answer. Okay.
Yeah, wait. This is the slight thing you have to understand. The data is composed of, it's like a table which has many rows. Let's say 1,000 rows, like in the iris example. I don't know how many.
Okay.
Rows. So you have like 1,000 rows. Each one of those rows is like one iteration. When you go over all the data for all of the 1,000 rows, then you call it one epoch, because you went over all the data once.
Okay.
And then you do it for like 100 epochs, or whatever number Lily set it to. So you have a lot of repetition. And the idea, yes, it's to improve whatever you're doing. In your case, you're trying to reduce noise. Here also, you're trying to reduce the error. And
Okay.
okay,
Yeah, you're saying rows for each record, and I'm talking about just keep running the results through. But okay, I see the difference, what you're saying.
yeah. So the epoch now is I hope it's understood. Okay, Lily, there was something else. Rebecca,
Sure.
what's the last thing? Do you?
Oh, it's okay. I'll read it.
Okay.
Carrying over the best results from one batch to the next. So when I'm talking about batches, so in that particular, like towards the end, when I'm saying batches, there's multiple batches, and each batch is living on a different GPU.
Mhm.
So when that's happening, that's like a part of a step during the whole training, like on layer 1 or layer 2 or layer 3. So after each layer, or like after a certain number of layers, sometimes depending on what you're doing, then they all have to come back together, and then like the gradient, which is the derivative, is computed after we compute whether or not, like what the error is. And then it's like for each how do you correlate between the batches? So the way that, like, after each iteration, that the error, like the difference between what you predicted and what the right result is, that is being like recorded, and that's being stored, and then using that changes like the weights and the biases. So then you're running the model over again.
Okay, I understand. I wasn't clear on what batch was. I thought it was just a large data set that was spread across different CPUs. But I understand what you're saying now. So you're trying different methods and you're going to compare which one is the best for that particular question that's being asked. Is that the correct understanding?
When I was talking about batches, that they're spread across different GPUs, but they're all coming back together when we're trying to compute each, like what was the result. So so with like when you're distributing the model across the different GPUs, then for like the error is computed on the GPU itself, and then the result of that is being aggregated together all at one central point, and then the average of that is being distributed across all the GPUs and then run through again. That's FSDP. And then with distributed data parallelism, DDP, then let's see, then after, so then that the data is getting processed through the GPUs, and then let me think, and then the gradient is getting computed all together, I believe.
Okay, so how do you pick the model of best fit? How do you pick the best model?
Rebecca, you don't pick the best model here.
Yeah.
Okay, it sounds like a
telling
lot.
that in the very beginning, like like during this whole entire talk, I didn't change my model. What I changed was the learning rate, the hidden layers. Those are the two things that I changed. So in the very beginning, when you know you're picking, like you're doing like a yes or no, or you're predicting like the next word, or depending on what you need to predict, then you pick your model based on that. But that would be another whole entire different talk, like picking your model,
Okay.
because there are also like other tools that you use where, like with RayTune, you could have different models that you could probably run through if you wanted to.
Okay, so batch then is a large data set run across different CPUs. Is that the correct understanding?
GPUs.
I don't want to confuse you further, but batch actually has a certain number of records in the data that you have, which
right. Hey, Jacob, can I try to answer that?
Try.
So, Rebecca, hey, this is Cameron. So, I'll use the example of my CNN that I did for facial emotion recognition. So I fed it in images and it spit out happy, sad, angry, neutral. And the batch size that I found was optimum was 64 images. And less than that, I think of the batch size. I don't know if this is technically correct, but the way I picture, so the batch is the number of images that I would put through each classification. And the batch size contained clues, a certain number of clues for the model to figure out the answer based on. And what I'm not sure about is why, like 128 batch size did not perform as well for me as 64. And 32, a batch size of 32 images contained too few clues, whereas a batch size of 64 was ideal. And I don't remember what happened at 128. It didn't get better. So I went back down, I think. But in any event, it's basically what what I want to say is it's so Jacob gave a great definition of epoch, right? Or the epoch. And so I would feed through each, I did 60 epochs back and forth through the neural networks. And in each epoch, the optimum that I found, the Goldilocks zone, not too hot, not too cold. The ideal zone to be was a batch size of 64. And the other thing, I was driving during most of this talk, but what I really wanted to do was drop in, have you heard of 3 blue, 1 brown, Rebecca?
No, I have not.
It's this YouTube that by this mathematician who has created an amazing visualization approach to visualizing what Lily is describing here. And you've got to see it, because it would, I mean, I think you learned enough here to be kind of vaguely understanding of what's going on. But if you watch that, it would all, like everything that Lily said here would make total sense. So if you drop your email, I'll ping you a 3 blue, 1 brown link. I don't know why he calls
Here,
himself that, but
yeah, I found the link. It's I just posted it. Yeah, I really like it.
is it the one on back propagation?
I think
There's
there's like
one
3 chapters. Like the first one is on deep learning, the second one, gradient descent.
Yeah.
I'm learning too much AI here. This is not okay.
The
No, well,
specific,
thank you for sharing that, Cameron, because it's kind of churning the wheels in my head. I vaguely remember an assignment in one of my classes that talked about something about this. And now it's piquing my curiosity, like, okay, how does this work? So yeah, you
Found
said
it.
3 blue, 1 brown on YouTube.
Yeah, I actually found it. Yeah, it's
oh,
on
perfect.
messages.
Yeah.
Okay.
Thank you.
Okay. Thank you.
Rebecca, and one thing at the end, it's like I'm going back to why Lily started all of this. She showed you first at the beginning the complexity of building clusters and how complicated it is, and later she showed you that Ray was very, very easily can do it very easily without all this complication. So this is one of the first things she showed you. Later on, she showed you that, oh, you can do machine learning with it. Oh, you can do even special machine learning with it and use the parallelism to do several things. She gave you acronyms and stuff like that. But your last question was related to whether you need to spread the data. So there is something that Lily didn't touch too much, or maybe she touched the beginning, but I want to bring it back now. Those models are large. We did talk about it. And the thing is, today on a regular GPU, let's say that has if you have a GPU on a gaming machine, you have like 12 gigabytes, which is, this is like a, I don't know, this is like a home machine will have 12 gigabytes. The models today, the large language models, only very few will fit into 12 gigabyte memory. It just will not fit. You need like a larger GPU. But then you have those huge models that you can't even fit in one GPU. Then you need to spread things around. Here, she's showing this. Then you need to actually spread it so the model will load it all. And this is where all those techniques become important. And she just showed you all the correct tools so you can do this. Otherwise, you won't be able to train them at all. Now, not that any one of us will be probably training those things, because the amount of time it takes to train is like a long time, even if you have a good GPU. And even if you have many GPUs, it still takes a huge amount of time to go over all your data. But still, she showed you all the techniques and abilities that are needed. And here, she shows you. You see?
Yeah, I'm looking at it. Mm-hmm.
So this is where you're asking about the memory thing. You can split the model, you can split the data, you can do all sorts of tricks, either to, in both cases, either to allow doing something that was impossible or to speed it up. And the set of tools she showed you, she showed a lot today. The set of tools is very useful for that. Am I correct, Lily?
Yeah, and I want to make a clarification that every time I'm talking about training on a GPU, I'm talking about your graphics card, because like your graphics card, when it is processing matrix multiplication, it's doing that much faster than your CPU. And towards the end, I did talk about serial offloading, where you can offload some of the data that's stored that's unused onto your CPU. But everything that you're seeing here, DDP is being, like, the data is being distributed. Your entire model is living on each node, and the FSDP is your model getting split and your data also getting split at the same time. Right, yes, that's what I was showing. And I didn't even touch too much upon. So this is all about, like, if you wanted to train your large language model from scratch yourself, and your large language model is larger than, let's say, like, like a handful of millions. So like maybe larger than 5 million parameters. So today, remember, we had 4. But if your model is more than 5 million and it's a transformers model, you're going to need multiple GPUs. But that's different. Training is different from inference. Inference is when you take an existing model and you could access it through an API. Like OpenAI has an API that you could just get an API key and you could just access it through a web request. And when you're like just making the prediction, you don't need as much GPUs. So this talk is more specifically on what it would take for a company to train large language models. But if you're running a large enough model, you would also need a good amount of GPU as well, just to do the prediction.
Yeah. GPUs are about 10 to 20 times faster than the CPU, even if you have a fast CPU. It's just because a GPU has many more small cores in them. They have like thousands, while your CPU has like, I don't know. If you have a good one, then you have like 30 threads, or like it's like 16 cores. If you have a very advanced machine, you have more, but like it's like big servers. But GPUs are like have many tiny elements there.
Yeah, for matrix multiplication, that's like important. Sorry.
So, like Lily, were you able to specifically train on NVIDIA GPUs anytime here, or like were you just like was there any difference you saw when you were using that?
No, we couldn't actually train on any NVIDIA GPUs using the Colab notebooks. You could enable them, but I didn't enable them during this presentation at all.
Oh, that do they charge extra for that?
No, they don't charge extra, but it's very limited in terms of what you could use.
Because like most of the like because that's what they always advertise, that NVIDIA has the best AI GPUs and processor and graphics card. So that's the reason I was trying to see which would be the best one to train using NVIDIA. That's
You want best? I'd say an A100.
Yeah, like that's, yeah, I think H100 is also really large scale, but you could enable it. Like I could enable T4 GPU right now. I just didn't do that.
Yeah.
And then you could
just
purchase it here.
One tangible example for everyone with the if you could keep the screen up, Lily. When for my 15,000 image data set, I had a 7-layer CNN, 15,000 images. And when I was on the if Lily had clicked the CPU, doing 60 epochs took 3 days. And when I switched to the A100, it took, guess how long?
3 hours.
45 minutes. It was but now the gotcha is, and when I met a guy who worked for Google at this conference, Google Cloud, at this conference in Austin in October. The first thing he was at lunch with at my lunch table, and I said, "Oh, you work for Google Cloud?" I said, "You owe me $104.25 because so I signed up through this Google Pro, and bought 100 hours, no, or how many hours? Yeah, I think 100 hours of GPU time. And I don't know how. So we would expect 60 seconds is 1 minute, 60 minutes is 1 hour, right? That's my definition of time. Well, I had planned on all these experiments to run to get my accuracy up before the deadline. I used up those 100 hours in like 24. It was so frustrating. I don't know how they calculate, but apparently they calculate memory you use with it. Well, how would I know that? And how could I like plan for that? But anyway, so that's just a little gripe. So if you if you click those GPUs, you won't really know when you run out unless someone knows the secret for how they bill.
Yeah, cloud. They should break that down. The cloud services. That's how they make their money, is by itemizing and simultaneous.
Oh yeah, and I'm used to doing that for cloud. I've done a lot of that for cloud
Yeah.
services, like normal cloud services, but not not for switching CPUs. Usually, I just select CPU and set it up at the very beginning, and I don't think about it after that. Unless we need more, but but when you're dealing with GPUs and CNNs, and it's a whole different ballgame, I guess. But
Yeah, that's why, like, I heard it's still a lot better if you could just have your own GPUs. So I have like friends, they'll like shell out like a couple thousand easy just to purchase like like one of the like Tesla GPU, like NVIDIA GPUs, and then that runs much faster on a desktop machine. But like the desktop machines, they might only have slots for a certain amount of GPUs. So that's when the whole like concept of nodes come in, and then you could use Kubernetes or Slurm, or there's a number of frameworks, or you could use Ray to connect all those nodes together. So then you could run them locally from home.
The limit also is power, Lily. GPUs consume, even the bigger ones, the bigger they are and the more memory they have, they consume more power. Even and power becomes the limit. You need a machine that has enough cooling and enough power supply so it will actually work. You can actually plug in multiple GPUs there. It becomes an issue. So you do want maybe multiple machines and nodes, and then you have to parallelize, and this is where all of your techniques that you showed us become very, very handy. But this is for most of us, it's mostly theoretical, unless some of us will do this, and hopefully some of us will actually end up in some company that has resources, and then you have to use those techniques, and then you've seen Lily's presentation and know how to start. Lily, since it seems that we're little by little leaving the topic and starting also random talks, do you want to add some last few words before I end up the recording?
No, I don't really have anything else to add, but yeah, thank you. Yeah, thanks everybody.
Okay. So let's thank you again, and don't go away. Please clap, make some noise, and don't go away. We're sticking around and we'll be talking about some other things. I just have to end up the recording. Give me a second. I have to find it.
Thank you.
Here we go. No, thank you.
Oh, shoot.
And